So this is linear algebra lecture 2. What we did in the first lecture is cover sections 1.1 and 1.2, where we were looking at one linear equation. So it's an equation of the form a1x1 plus a2x2 up to an xn equals b. So this is one linear equation in n variables. You can have any positive number of variables. This equation is called homogeneous if b is equal to 0, and inhomogeneous if b is not equal to 0. And we write a solution in the form of an n-dimensional column vector. So this is a solution of this equation. And the set of all these n-dimensional column vectors is written R superscript n. So this is n-dimensional column vectors where the coordinates x1 up to xn are real numbers. And this is an example of a vector space, which I'll define, I think, officially tomorrow. This is, in some sense, the most important example of a vector space. And so, for example, if you have the equation 2x1 plus 3x2 minus 7x3 equals minus 13. One solution of this is, for example, let's see, what would be a solution? Minus 1, 1, 2, I think, is a solution in R3, because 2 times minus 1 plus 3 times 1 minus 7 times 2 is minus 2 plus 3 minus 14, which is minus 13. So that's an example of a solution. And we define how you add and subtract vectors. If you have vectors x1 down to xn and y1 down to yn, you define addition coordinate-wise. And so this is vector addition in Rn. And if you take a vector and you multiply it by a number c, and in linear algebra, a number is called a scalar, you multiply a vector by a scalar by multiplying every coordinate by the scalar. So this is an operation of scalar multiplication in Rn. A subspace of Rn is a subset W contained in Rn, which has the following 3 properties. First, the 0 vector is in W. The 0 vector is simply the vector where all the coordinates are 0. If x and y are in W, then x plus y is in W. So the set W is closed under vector addition. And if x is a vector in W and c is a scalar, a real number, then c times x is in W. So a subspace is a set of vectors containing 0 that's closed under vector addition and scalar multiplication, and the solution space, which means the set of all solutions of a linear equation, is a subspace. Okay. If you take a vector, let's say x in Rn, and a subset W of Rn, then we have the translate of W by X. It's just the set where for every vector W in the set capital W, we take X plus W. So you add X to every vector in W, and that's called the translate of W by X. And we write that as X plus W. And what is called an affine subspace of Rn is the translate of a subspace of Rn. And the solution space of an inhomogeneous equation is always an affine subspace. So, for example, let's see, let me pick an example from the notes so it's easy for you to understand this when you are studying it. Well, I'll just make up an example. Suppose you have the equation 4x plus 5y equals 2. And we want to find all solutions of this inhomogeneous equation. So high school algebra always is good. You can solve this equation for y. 5y is 2 minus 4x. So y is 2/5 minus 4/5 x. So no matter what number you pick for x, if you choose this value for y, you get a solution of this equation. So the vector xy is a solution if for any x, y is 2/5 minus 4/5 x. Let me sort of exaggerate slightly. Let me write, so this is the second coordinate is 2/5 minus 4/5 x. X is the same as 0 plus 1 times x. So if I write it like this is just to help me see that this is the sum of two vectors. 0, 2, 5 plus 1 times x minus 4/5 times x, which is the same as the vector 0, 2/5 plus x times the vector 1 minus 4/5. So what this tells us is that the vector xy is a solution of the inhomogeneous equation 4x plus 5y equals 2, if and only if xy is a vector of the form, it's this vector 0, 2, 5 plus any scalar multiple x of the vector 1 minus 4 over 5. Now, if I let w be the set of all scalar multiples of the vector 1 minus 4 over 5, this is a subspace of R2. Because if you add two scalar multiples of a fixed vector, you get another scalar multiple of the vector. So this is a subspace of R2. And so the solution space is this fixed vector 0, 2, 5 plus x. So the solution space of the equation 4x plus 5y equal 2 is the set, call it L, which is the vector 0, 2, 5 plus w. It's all vectors which are a translate of something in w by the vector 0 to 5. So this is an affine subspace. So no matter what I pick for x, I get a solution of this equation. So the simplest solution, for example, if I let, I can let x be anything. So, for example, let x be equal to 1. If x is equal to 1, y what was the expression? Y is 2/5 minus 4/5 x is 2/5 minus 4/5 times 1 is minus 2/5. And let's just check. 4 times 1 plus 5 times minus 2/5 is 4 minus 2 is 2. So this does check. This is a solution. So this is just an example of the fact that the solution space of an inhomogeneous equation is an affine subspace. Right? That's what we wanted to know. All right, any questions about this? This is all kind of review of what we talked about yesterday. Okay, that's one linear equation, but already in pre-calculus, if not high school, or maybe that was even in high school, you dealt with systems of equations. So that's what I want to talk about next. So this is section 1.3. Systems of linear equations. So you're used to solving equations, a system like 2x plus 7y equals 3, 5x minus y equals 8. Right? Find all solutions of this system of two equations and two unknowns. Right? And you probably learned how to do this before you started Lehman. For example, you could eliminate the y. Here's the first equation. Take the second equation and multiply it by 7. Add, the y's cancel. You get 37x equals 59. So x is 59 over 37. And if x is 59 over 37, for example, from this equation, this says y is equal to 5x minus 8. So that's 5 times 59 over 37 minus 8, which is what? I don't know. Let's see. 5 times 59 is 295, I think, over 37 minus 8. If you write 8 as over the denominator 37, 8 times 37, 8 sevens are 56, 8 threes are 24, 29. Huh. Maybe this is minus 1 over 37. Let's see. Let's just check. 2x plus 7y is 2 times 59 over 37 plus 7 times minus 1 over 37. This is 118 over 37 minus 7 over 37, which is 111 over 37, which by a miracle is 3. So this does solve the first equation, and 5x minus y is 5 times 59 over 37 minus 1 over 37 is 295 over 37 plus 1 over 37 is 296 over 37, which we already saw was 8. So we actually did find a solution. So in fact, there's a unique solution. So this system of equations has the unique solution. Xy equals 59 over 37 minus 1 over 37. All right, so if you haven't solved systems of equations by hand in a long time, you'll certainly get a lot of practice in linear algebra. All right. Any questions up to this point? Okay. So in general, a system of linear equations in variables, let's say you have m linear equations in n variables. So your first equation you can write as a11x1 plus a12x2 plus a13x3 up to a1nxn equals b1. That's one equation in n variables. Second equation we would write as a21x1 plus a22x2 plus a23x3 a2nxn equals b2. And we have m equations altogether. And the last equation would be am1x1 plus am2x2 up to amnxn equals b sub n. Right. So that's what a system of m equations in n variables looks like. And if you have the variable xj in the ith equation, we generally write the subscript, the coefficient of xj in the ith equation, with a pair of subscripts I and j, just the way I did this. You'll see this absolutely everywhere in the notes. And a solution is a vector, x1 up to xn, in Rn that solves all of the equations simultaneously, just as we saw in the example. Okay. So we say the system is homogeneous if, when you look at the right-hand sides, the B's, this column vector, they're all zeros. The column vector is the zero vector. So the system is homogeneous if every single one of these numbers on the right-hand side is zero, and it's inhomogeneous if one of these numbers at least is non-zero. So if any one of those numbers is different from zero, then the system is called inhomogeneous. So let's take an example. Here's a system x plus y plus z equals 0 for x minus 3y minus 10z equals 0. So here we have two equations. In three variables, x, y, and z. And it's homogeneous. It's a homogeneous system because the right-hand sides are both equal to 0. Let's try and find the solutions. Well, the simplest way is just to play with the equations and eliminate some variables. So suppose I want to eliminate x. I can multiply the first equation by 4. And write down the second equation. And if I subtract the second equation from the first equation, I get 7y plus 14z equals 0. Or I can divide by 7, y plus 2z equals 0, or y equals minus 2z. So this tells me that for any solution of these equations, y has to equal minus 2z. If I look at the equation like this first equation, x plus y plus z equals 0, y has to be minus 2z, so x minus 2z plus z equals 0, or x minus z equals 0, or x has to equal z. So in any solution of these equations, the solution vector x, y, z, x is going to be z, y is going to be minus 2z, and z is z, which is simply z times the vector 1 minus 1, 1. Sorry, this is a 2. 1 minus 2, 1. Which says that, and no matter what I pick for z, I get a solution of the equation of the system. And every solution is of this form. So the solution space, the set of solutions of this equation, is W as the set of all scalar multiples of the vector 1 minus 2, 1. And this is a subspace of R3. Just all scalar multiples of a fixed vector. And this is a general phenomenon. So there are two theorems, which I'll just write in one space. The solution space this theorem, I think 1.4 in the text. the solution space of a homogeneous system of linear equations is a subspace. So when you have a homogeneous system of equations, the set of solutions, the solution space, is always a subspace. If there are n variables, it's the subspace of Rn. Now, for a system of inhomogeneous equations, there's one strange thing that can happen. Suppose we have the system of equations x plus y equals 0, and the second equation is x plus y equals 1. So this system has no solution, because x plus y can't be equal to 0 and 1 at the same time. So a system with no solution is called inconsistent. So an inconsistent system of equations is a system that has no solutions. Like, here's an example. But if the system is consistent, which means it has at least one solution, the solution space of a consistent inhomogeneous system is an affine subspace. It's a translate affine, I-N-F-I-N-E. It's a translate of a vector subspace, an ordinary subspace of Rn. So this is exactly what we saw for one equation. If you have one equation, it's homogeneous, the solution space is a subspace. If it's inhomogeneous, the solution space is an affine subspace, with the understanding that some inhomogeneous systems are inconsistent, which means they have no solution. If there is a solution, if the system is consistent, then the solution space of the inhomogeneous system is always an affine subspace. So these are sort of fundamental facts, almost geometrical facts in algebra about linear equations. Okay. Any questions so far? Now, there is a kind of algorithm to solve a system of linear equations. If you're a computer science student, you can write a computer program for this. And the algorithm is called Gaussian elimination. And this allows you to find all solutions of a system of linear equations. And what if the equations are inconsistent, have no solution? Then this algorithm of Gaussian elimination will tell you the system is inconsistent. So Gaussian elimination finds all solutions of a system if there's a solution, and tells you if there is no solution. So we start with the notion of equivalent systems of linear equations. So two systems of equations in n variables are equivalent if they have exactly the same solutions. That is, a vector solves one system of equations if and only if they solve the other system of equations. So it's a homework problem to show that if you look at the system 7x minus 2y equals 10 and 3x plus y equals 21, that's one system of equations in two variables. If you look at 4x plus 11y equals 115, x plus 7y equals 67, and 8x minus 5y equals minus 13. The important thing is they have the same number of variables. Both of these systems have two variables, x and y. The number of equations in the systems does not have to be the same. And in this case, they're not the same. Two equations, three equations. But the important thing is they have the same number of variables. And it turns out they have exactly the same solutions. In fact, there's a unique solution, as it turns out. So both systems have the unique solution xy equal to 4, 9. Right? That is, you find all solutions for this system, there's just one, 4, 9. Find all solutions for this system, there's just one, 4, 9. That means the systems are equivalent. Okay. So this is an important idea to get in your head, and it requires some thought. It's not something that I think you can absorb instantly. The problem with summer school is you don't have a lot of time to absorb new concepts. So you need to be thinking about this stuff all the time and try to make it familiar. So suppose you have a system of equations. It turns out there are exactly three, well, there can be more than three, but I'm going to write down. There are three elementary operations on a system of equations that produce equivalent systems. So you have a system of equations, you do something to them to get a new system of equations, but they are equivalent. They have exactly the same solutions. So what are these three elementary operations? Well, they're actually really elementary. So let me give a sort of a silly example. Here's a system of equations we just saw. 7x minus 2y equals 10. 3x plus y equals 21. That's one system. Suppose I interchange the two equations. I write the second one first, and the first one second. Right? So all I did was interchange the two equations. These are different systems because in the first system, this is the first equation, and in the second system, this is the first equation. And in the first system, this is the second equation, but it's, and in the other system, this is the second equation. But all I did was interchange two equations. So any numbers x and y that solve both these equations also solve both these equations. So this is the first elementary operation. I can call it just interchange. You can interchange any two equations. and we get an equivalent system. Okay. What else can we do? Well, from this system of equations, I could get another equivalent system, for example, by doing the following. Suppose I multiply the first equation by some number, like, I don't know, 5. So then I would have, instead of 7x minus 2y equal 10, if I multiplied the equation by 5, I get 35x minus 10y equals 50. And I am not changing the second equation. Now, this system is different from this system because the first equation is different. This has 7, this has 35. But the way I got this equation from this, I just multiplied the whole equation by 5. So any solution of this system is still a solution of this system, and any solution of the second system is a solution of the first system. That's all we're doing. That's the second elementary operation. It's I'll call it multiplication. You can multiply any equation by a non-zero number, a non-zero scalar. That's the second operation. I said there are 3. What is the third? This I'll call, let's say, replacement. So let me give an example. So suppose I have 7x minus 2y equals 10, and 3x plus y equals 21. That's my original system. Suppose I don't change the second equation, but I add, let's say, 2 times the second equation to the first equation. So 2 times 3 is 6, 6x plus 7x is 13x. Multiply this by 2, 2y minus 2y is 0. Multiply this by 2, 42 plus 10 is 52. So what I did is I added 2 times the second equation to the first equation. And I claim these systems have exactly the same solution. Because if xy solves both of these equations, if I add twice the second to the first, I'm just adding twice 0 when I plug in that x and y. I don't change anything. And conversely. So replacement means this is the operation. Choose one equation. And add to it a non-zero scalar multiple of another equation. See, that's what I did here. I chose equation 1, the first equation, and added to it 2 times the second equation. That's how I got from here to here. This equation plus 2 times this gives me that. So these 3 operations on a system of equations give you a new system of equations with the same solutions. And the strategy of Gaussian elimination is to pick a sequence of these elementary operations that you apply to a system to make the system easier and easier to solve. And because the systems have the same solutions, when your system is so easy to solve that you can actually just solve it by looking at it, you're done. You win. So the best way to understand this is to work in some examples. So let me do that. So this is Gaussian elimination is an intelligent way to pick the sequence of these elementary operations to solve the equations. Right? And there's a very long and complicated explanation in the text because it's hard to put into words, but when you see an example, it becomes easy. So here's a system of equations. 9x plus 11y equals minus 1. And 5x plus 6y equals 3. So look at the first variable, which has a non-zero coefficient, that's x, and it's already in the first equation. Multiply the first equation. I want to have the coefficient of x to be 1. So I want to multiply equation 1 by a ninth. If I multiply this first equation by a ninth, I get x plus 11 over 9y equals minus 1 over 9. And my second equation, I don't change. So I performed one elementary operation on this system. I multiplied the first equation by a ninth. So now the coefficient of x is 1. Now I'm going to eliminate x from the second equation. So my first equation is x plus 11 over 9x equals minus a ninth. I'm going to add minus 5 times the first equation to the second. So add minus 5 times equation 1 to equation 2. So minus 5x plus 5x is 0. Minus 5 times this, that's minus 55 over 9y plus 6y equals, let's see, I'm multiplying by minus 5. Minus 5 times minus a ninth is 5 ninths plus 3. Or if I do my arithmetic, this is my first equation. I didn't change from here to here. 6 is the same as 54 over 9. So this is minus 1/9 y equals 27 plus 5 is 32 over 9. Okay. So here's my original system of equations. I performed one elementary operation to get this system. I applied a second elementary operation to get this system. I can multiply an equation by a non-zero scalar. I want to have the coefficient of y equal to 1. So I want to multiply the second row by minus 9. So the first row is still x plus 11 over 9y equals minus 1 over 9. If I multiply this row by minus 9, I get y equals minus 32. Okay. And again, this new system has the same solutions as the old system, which tells me, first of all, that in any solution, y has to be minus 32. Let me eliminate this y. So the second equation is y equals minus 32. Suppose I add minus 11 over 9 times row 2, or equation 2, to equation 1. So I get x plus 0, minus 11 over 9 times 0 is 0. This is x. Minus 11 over 9y plus over 11 over 9y is 0. I just get x equals minus 11 over 9 times minus 32 over 9 added to -1/9. That's what x is. Let's see, let's do some arithmetic. 32 times 11 is 352 minus 1. So this is minus 353. This way? Sorry, no, minus plus. It's minus 352 plus 352 minus 351. 351/9. 351/9. 9 goes into that. 3, 7, 8, yeah. This is 39. So we get x equals 39, y equals minus 32. So by performing this sequence of elementary operations on a system of equations, the solutions of this system are the same as the solutions of this system. But this is just 39 minus 32. That is the solution of this system of equations. So we've solved the original system of equations. So what was the procedure we were going through? What was our strategy in this? What is Gaussian elimination? So you have your system of equations, a11x1, a12x2, a1n xn, down to am1x1, am2 x2, amn xn is equals b1 equals bn. This system of equations. Now, some of these coefficients, the a's can be 0. So find, in all these equations, find the variable, and this is a non-zero system. If all the a's are 0, there's no solution, or everything is a solution. So if some coefficient aij is non-zero, find the smallest index j such that xj occurs in some equation with a non-zero coefficient. So somewhere you have aij xj, and aij is not 0. So xj occurs with a non-zero coefficient, and find the smallest value of j. Maybe. So like if x1 occurs with a non-zero coefficient, it's going to be x1. Now, so you have this a1j xj has a non-zero coefficient. It's in the ith equation. It's not necessarily in the first equation. So interchange equations, so the ith equation and the first equation are switched. So this now is somewhere in the first row. So you have xj in this first row with a non-zero coefficient. And everything to the left is 0, because j is the smallest number for which the variable xj has a non-zero coefficient in some equation. Then you multiply this equation by whatever makes the coefficient of xj equal to 1. So this is 1. And then you can subtract multiples of that from all the other equations to eliminate xj from all the other equations. So now you have an equivalent system where the first equation has xj, and all the other equations, there's no xj in them. The smallest subscript for which the variable might have a non-zero coefficient is j plus 1. And you can sit and you iterate this process. You continue this process, and it will, at some point you stop. You can't go any further, and then you'll have solved all your equations. So again, let me do another example, because this is, as I emphasize, the only way to understand this process. So Let's take another example. Let's take the following system of two equations and three variables. 2x plus 3y plus z equals 1, and 5x plus y minus 4z equals minus 1. So that's our system. We can think of x, y, z as like x1, x2, x3, ordered like that. So x occurs with a non-zero coefficient already in the first row. So I want to make this coefficient of x1 to just multiply the first row by a half. You get x plus 3 halves y plus a half z equals a half, and 5x plus y minus 4z equals minus 1. So x occurs with coefficient 1. Then I want to eliminate x from the second equation. So here's my first equation. I'm not changing it. X plus 3 halves y plus a half z equals a half. And I subtract 5 times the first row from the second row. So 5x minus 5x is 0. Y minus 5 times 3 halves, that's 15 halves. 1 minus 15 halves is minus 13 halves. And minus 4 minus 5 halves is minus 13 halves z, and minus 1 minus 5 halves is minus 7 halves. So that's my, here I did scalar multiplication of the first equation by a half. Here I added 5 times the first, minus 5 times the first equation to the second equation. I eliminated the x here. Now, not looking at the first equation, in the other equation, the first variable with a non-zero coefficient is y. I want to make the coefficient 1. So I multiply the second equation by the reciprocal of minus 13 halves, which is minus 2/3. So my first equation still doesn't change. X plus 3 halves y plus a half z equals a half. If I multiply by minus 13 halves, I get y plus z minus 13, minus 2 over 13 is equal to 7 over 13. And then I want to eliminate y from the first equation. So my second equation doesn't change. But I take the first equation minus 3 halves times the second equation. So x minus 0 is x. 3 halves minus 3 halves is 0. 1 half minus 3 halves is minus 1. So minus z. And 1 half minus 3 halves times 7 over 13. 1 half minus 3 halves times 7 over 13 is 1 half minus 21 over 26. This is 13 over 26. So this is minus 8 over 26, or minus 4 over 13 equals minus 4 over 13. And now I look at these two equations. The first equation with a non-zero coefficient, and the first variable with a non-zero coefficient in the first equation is x, and the second equation is y. There's nothing else I can eliminate, but from this says what? This says that x is equal to minus 4 over 13 plus z. and y is 7 over 13 minus z. So in any solution x, y, z, x and y satisfy these conditions. So my solution, every solution of the system of equations is of the form x is minus 4 over 13 plus z. Y is 7 over 13 minus z, and z is equal to z. And I can write this as follows. You can always add a 0. This is the fixed vector minus 4 over 13, 7 over 13, 0, plus z times the vector 1 minus 1, 1. So every solution of this system of equations is of this form. And if I look at this set of vectors for all z, that is an affine subspace. The set of all vectors of this form is a vector subspace. And then I'm translating that subspace by this fixed vector. Okay. Maybe just to give you a little bit of immediate practice. Suppose we take the system of equations 2x plus y plus z equals 0, x plus 2y plus 3z equals 0. So spend a couple of minutes by yourself right now and use Gaussian elimination to find all solutions of this system of 2 equations and 3 variables. It's a homogeneous system because the right-hand sides are both 0. So the solution will be a vector subspace. And you should try to find it. So I'm going to pause the recording for a minute and give you a chance to start, and then I will go through it myself. See, how do you start? Well, the first variable with a non-zero coefficient is x, and you're likely to have a coefficient of 1, so there are 2 things you could do. You could multiply the first equation by a half, and then you get a 1 times x. Or you could interchange the 2 equations, because here x occurs with a coefficient of 1. So one choice is not better than another. I prefer to interchange these equations, so I don't have to deal with fractions right away. This is x plus 2y plus 3z equals 0. 2x plus y plus z equals 0. So what I did was interchange the 2 equations. And now I want to eliminate this x from the second equation. So my first equation stays the same. But I'm going to add minus 2 times the first equation to the second, or equivalently, I'm going to subtract twice the first equation from the second. So 2x minus 2x is 0. Y minus 2 times this, that's y minus 4y is minus 3y. Z minus 6z is minus 5z equals 0. That's what I get. Now, in the second equation, I want to make the coefficient of y 1. So don't touch the first equation. Multiply the second equation by minus a third. I get y plus 5/3 z equals 0. Okay, so now here the first coefficient is 1 for the variable y. And I want to eliminate 2y from the first equation. So my second equation doesn't change here. But I take the first equation minus twice the second. X minus 0 is x. 2y minus 2y is 0. So it's the first equation minus twice the second. So 3 minus 10/3. 9/3 minus 10/3, that's minus 1/3 z equals 0. And now I'm finished with Gaussian elimination. Each equation starts with a different variable with coefficient 1, and those variables don't occur in the other equations. There's no x here, there's no y here. So, but what's the solution of this system? The solution of this system is x equals 1/3 z, y is minus 5/3 z, and z is just z. So for any solution of this system, x, y, z is equal to 1/3 z minus 5/3 z, or z times the vector 1/3 minus 5/3 1. So for this system of equations, the solution space, W, is the set of all scalar multiples of the vector 1/3 minus 5/3 1 for all z in R. So this is a subspace. Sometimes just to emphasize that it's a subspace, but not a real affine subspace, we can call this a vector subspace. But the solution of this system of equations is a subspace. Now, we should check that I didn't make any mistakes. So we have x, y, z equal to 1/3 minus 5/3 1. So 2x plus y plus z is 2 times 1/3 minus 5/3 plus 1. This is 2/3 minus 5/3 plus 1 is 0, so that checks. And the second equation, x plus 2y plus 3z, so x is 1/3 plus 2 times minus 5/3 plus 3 times 1. So that's 1/3 minus 10/3 plus 3 is minus 3 plus 3 is 0, so that also checks. So it works. We win. We did it right. All right. So this is Gaussian elimination, and there are several homework problems where you have to solve systems of equations using Gaussian elimination. It's definitely the case that the more you practice with this, the better you get at it. And yes, wait. Okay. There's one more important theorem about linear equations that I want to state and prove right now. And that is the following. So suppose we have a system, a homogeneous system of m equations in n variables. So for example, you might have m equal n equals 2. So you have the system 3x plus y equals 0, and 5x plus 2y equals 0. And you want to solve this system. Let's just solve it. So let me solve it using Gaussian elimination. That's fun. X plus a third y equals 0, and 5x plus 2y equals 0. I just multiplied the first row by a third. Then I take the first row minus the second equation minus 5 times the first equation. 5x minus 5x is 0. 2y minus 5/3 y is a third y equals 0. Then I multiply the second row by 3. And then I add minus a third times the second row to the first row, or I take the first equation minus a third times the second equation. I get x equals 0, y equals 0, which says the only solution of this system of equations is x equals y equals 0. So this system of equations has exactly one solution, the zero solution, or you might call it the trivial solution. In general, if you have a homogeneous system, a11 x1, a1n xn equals 0, m equations, so the last one is am1 x1 plus amn xn equals 0. If you have this system of equation, this always has the zero solution, which is called the trivial solution, where x1 up to xn is just all zeros, right? Because if you let all the x's equal 0, you just get 0 equals 0. Letting all the x equal 0 is a solution. So a homogeneous system always has the trivial zero solution. But sometimes it has a non-zero solution, a non-trivial solution. And the very big theorem says the following. I'll call this is a big theorem. If there are more variables than equations, if n is bigger than m, n is always the number of variables in the system. M is always the number of equations in the system. If n is bigger than m, then the homogeneous system of equations has a non-zero or non-trivial solution. So if instead of 3x plus y equals 0, 5x plus 2y equals 0, suppose we had the system 3x plus y plus z equals 0, 5x plus 2y plus minus z equals 0. So here we have a homogeneous system. M is equal to 2 equations. N equals 3 variables. 3 is bigger than 2. There are more variables than equations. So this system has to have a non-zero solution. Let's check. Let's solve the equations. So I have 3. I'll use Gaussian elimination again. It's supposed to work. So I multiply the first equation by a third. And here's the second equation. Then I don't touch the first equation now. But I take the second equation minus 5 times the first equation. So that cancels the x. 2 minus 5/3 again is third y. Minus z minus 5/3 z is minus 1/8 z equals 0. That's what I get there. Now I multiply, I want to make the coefficient of y in the second equation a 1. So I multiply the second equation by 3. So my first equation is still x plus 1/3 y plus 1/3 z equals 0. Multiplied by 3, I get y minus 8z equals 0. Then I want to eliminate the y from the first equation. So my second equation is good the way it is, y minus 8z equals 0. Let me take the first equation minus 1/3 times the second equation. So x, 1/3 y minus 1/3 y is 0. 1/3 y, 1/3 z plus 1/8 z is 9/3 z plus 3z equals 0. So this original system of equations is equivalent to this system of equations. And in this system of equations, x is minus 3z and y is 8z. So, so the vector x, y, z, any solution is going to be of the form minus 3z, 8z, z, or z times the vector minus 3, 8, 1. So according to this is the set of all solutions of this system of equations. So in particular, minus 3, 8, 1 is a non-zero solution, a non-trivial solution. Let's just check. If I take 3x plus y plus z, that's 3 times minus 3 plus 8 plus 1 is minus 9 plus 9 is 0. In the second equation, 5x plus 2y minus z, that's 5 times minus 3 plus 2 times 8 minus 1. That's minus 15 plus 16 minus 1 is 0. So it checks. So this system of equations does have this non-zero solution. Yep. Nice to know. So this is an instance of what I just called the big theorem. If you have a system of homogeneous equations, n variables, m equations, and n is bigger than m, strictly more variables than equations, and in our case, we had 3 variables and 2 equations, then the homogeneous system of equations has a non-zero solution. How do we prove this theorem? That is what we have to do. So I'm now going to give a proof of what I just called the big theorem. So we have m equations and variables. I'm going to improve this by induction on M. So a proof by mathematical induction goes as follows. You prove it's true for some starting case, for example, M equal 1, and then and any number of variables. And then you show that if it's true for M equations, it's also going to be true for M plus 1 equations. So we start with M equal 1 less than N. So we have one equation and at least two variables. So the equation looks like A11x1 plus A12x2 plus A1n xn equals 0. I want to show there's a non-trivial solution to this one equation where n is bigger than 1. Now, we can say there are two cases. If A11 is equal to 0, if this first coefficient is 0, then if I let x1 equal 1 and all the other variables equal 0, I have a solution, because I would have 0 times 1 plus A12 times 0 up to A1n times 0 equals 0. And this is a non-trivial solution. This is a solution 1, and then everything else is 0. It's not the 0 vector. That's if A11 is 0. But if A11 is not 0, then whenever you have this equation, that's the same as A11x1 equals minus A12x2 minus A1 and xn. I just bring all of this to the other side of the equation, and then divide by A11, which I can do because it's non-zero. So I have at least one variable here because n is at least 2. So no matter what values I pick for x2 up to xn, if I define x1 by this, I have a solution of the equation. So I can choose some non-zero value over here, and that determines x1. So if you only have one equation and two or more variables, it's pretty simple to see that there is a non-trivial non-zero solution. So assume it's true for M equations in n greater than m variables. And now we have a system of m plus 1 equations. In at least n plus 1 variables. Actually, let me do it the way I did it in the notes, which is just to be, this will work fine, but let me just do it the way I did it in the notes. Suppose that m is at least 2, and the theorem holds for m minus 1 equations in n minus 1 variables where n is bigger than m. Must prove for m equations in n greater than m variables. So we have our system A11x1, A1n xn equals 0, down to am1 x1 plus amn xn equals 0. And we can make the following observation. First of all, look at all the coefficients of the x1s. So if all of those is 0, if ai1 equals 0 for all I, then we just have to let x1 equal 1 and xj equals 0 for all the other variables. J goes from 2 up to n. Because if each of these coefficients is 0, if I let x1 equal 0 and all the other variables equal to, if I let x1 equal 1 and all the other variables equal to 0, I get a non-trivial solution. So that's sort of like the trivial case. Otherwise, ai1 is different from 0 for some I. That is, one of these coefficients of x1 is non-zero. By interchanging equations, I can assume that a1 is not 0. So then I apply my Gaussian elimination process. I can multiply the first equation by the reciprocal of a1. So the first equation starts with a coefficient of 1 for x1. Say x1 plus a12 prime x2 up to a1n prime xn equals 0. And then subtracting suitable multiples of the first row from the other rows, I eliminate x1 from all of the other equations. So I get a new system which looks like this. So there's no x1 in any of these equations. Now, look at this system. Here I have m-1 equations. I threw away x1, so I have n-1 variables. n-1 is bigger than m-1. This has a non-trivial solution, a non-zero solution. So pick some x2 up to xn, not all 0, which make all these equations equal to 0. And then use those numbers to define x1. And I have a non-zero solution for this system of equations, which is equivalent to the original system. And that really completes the proof. Now, when I say it, it's sort of quick and I can speak more slowly, but that won't make any difference. The only way to understand this is to find some time and a quiet spot and sit down and read very, very carefully through the proof and maybe spend a lot of time working homework problems which give examples of what's going on to understand this. That's the whole secret of all of this. It takes time and effort and more time. But that's the proof of this theorem. And it's one of the basic theorems in linear algebra. It says if you have a system of homogeneous equations with more variables, strictly more variables than equations of a homogeneous system, then there must always exist a non-zero solution. And in fact, Gaussian elimination will allow you to find it, but it always must exist. That's the theorem and the proof. Okay. Any questions about this? We're covering a lot of material, but again, we just went through today a week's work in the regular semester, and that's the way summer school works. Okay. If not, then we're done for the day. Looks like a lovely day. Hope you can enjoy it a little bit. And I'll be back 9 o'clock tomorrow. Bye, all.